Hello, welcome to those of you who are just joining us now. We're going to give it a moment for folks to come into the webinar, and then we'll get started. All right, hello everyone. Welcome to this quick Quake briefing webinar on the 7.0 earthquake that struck offshore Cape Mendocino, Northern California last month. This is co-hosted with our Northern California regional chapter. My name is Elizabeth Angel. I'm EERI's Communications and Program Manager. And before we get started with our presentations today, I just want to take a brief moment to talk to you about EERI if you're not familiar with the organization. So we're the leading nonprofit that brings together people from a wide range of different disciplines, backgrounds, research, and practice who are all dedicated to the shared mission of understanding earthquake risk and increasing earthquake resilience in our communities around the world. So I encourage you to find out more about EERI. If you're not already a member, become a member. If you are a member, make sure you've renewed for 2025 so you continue to have access to our great programs. And you can find more about us on our website, eeri.org. I also want to acknowledge that this webinar series is made possible with support from the Federal Emergency Management Agency, by the Learning from Earthquakes Endowment Fund, and by EERI members like many of yourselves. And also by the support of our subscribing members who are listed on this slide. If you have interest in becoming a subscribing member, you can reach out and contact us. And finally, I just want to mention some upcoming webinars. We have one next week, which is going to be highlights of our Earthquake Spectra November 2024 issue, with a couple of great speakers talking about their papers from that issue. We have a reconnaissance webinar from our Learning from Earthquakes program coming up next month, shortly after the 2-year anniversary of the 2023 Kahramanmaraş earthquake sequence that struck Turkey and Syria. And that's going to be about findings from a follow-up reconnaissance team we sent in partnership with the Social Science Extreme Reconnaissance Events group back in October, and they were looking at housing recovery, reconstruction, et cetera, and sort of the longer term impacts of that earthquake. So that's going to be a great event. You can find more information and register for those by going to our website and checking the upcoming events tab. I should also mention quickly, it's not scheduled yet, but we're likely to do another webinar with the Learning from Earthquakes program focusing on this offshore Cape Mendocino earthquake and looking at some reconnaissance findings from that. So that will be announced in our Pulse newsletter and on the website once it's formally scheduled and there's a registration link. So stay tuned. And with that, I'd like to hand it over to Richard McCarthy, the president of EERI's Northern California chapter.
Well, welcome everyone, and thank you, Elizabeth. So our chapter is pretty active. We focus on educational programs such as you're seeing here that you'll hear from Bruce about in a few minutes. We also support our student chapters as well. And another thing we do is we track legislation in the California legislature. And I can tell you right now that there'll be a lot of action in the legislature based on these fires in Los Angeles. So again, thank you for joining us today. Bruce, would you introduce our speaker, please?
Thank you. Welcome to our briefing on the magnitude 7 earthquake that struck offshore California last month. My name is Bruce Mason. I am one of the executive board members of the Northern California chapter, and I will be serving as your moderator today. Now, our Quick Quake briefing program is a free webinar program. It's open to anyone. If you're a member of EERI, then you will get notifications of upcoming briefings. But if you're not, you can still get on our mailing list. And the way to do that is to send me your email address, and I'll put you on the list. Now, you can view our briefings live, like today, or you can see them on YouTube because they will be posted there. We have over 20 Quick Quake briefings posted on the YouTube channel. So now on to today's briefing. On December 5th, 2024, at about 11 o'clock in the morning, there was a magnitude 7 earthquake that occurred at the famous Mendocino Triple Junction. That's a point offshore Northern California where 3 tectonic plates meet. This was the strongest earthquake to hit California since the 2019 Ridgecrest earthquake. So on average, there's only about 20 earthquakes magnitude 7 or greater each year worldwide. So this was a significant event. However, there was very little damage from this earthquake, and the reason is the epicenter was about 40 miles offshore California. However, the earthquake triggered extensive tsunami warnings, and we'll be hearing about that later in our meeting today. Now, we're excited to have a speaker from the California Geological Survey. We originally had scheduled 2 speakers. However, our second speaker is involved with the tragic fire events that are happening in Los Angeles. So he was called away. So our speaker today will be Jay Patton, and he will cover both of the subjects, that is the seismology as well as the tsunami warning system that was activated. Now, the format for today's meeting is this. It's a 60-minute program. Jay will talk for about 40 minutes, and then the remaining time will be for question and answer period. Now, we encourage questions from the audience, and how you do that, you'll see at the bottom of your screen, there's a Q&A button. You press that and then type in your question. Then behind the scenes, Elizabeth and I will go over the questions, and I will return later in the program and pose your questions to our speaker. Now, we know there might not be enough time to handle all the questions, so our speaker today has kindly put his email address in his presentation so you can send questions directly to him, and in the coming days, he will try to answer your questions. Now, I would like to introduce our first speaker today, and it's a Dr. Jay Patton from the California Geological Survey. So Jay, could you please proceed?
Thank you, Bruce and Richard and Elizabeth. Thanks for having me here to present an overview of the tectonic background of these 3 unrelated earthquakes, though they are all part of the Pacific North America plate boundary system. I'll make this slide deck available to anyone who wants it so that people can go back and review many of the details that I don't have to completely discuss today. And my email is listed here as well as the last slide. So, click. So here's a map, a simplified map of Earth's principal tectonic plates, thin layers of the Earth that move around in different directions. And the red arrows indicate the direction of relative movement at the plate boundaries where these plates meet each other. We can see that California is inside the white box. Well, there are 3 types of plate boundaries: divergent, where plates move away from each other; convergent, where plates move towards each other; and transform, where plates move side by side, like the San Andreas Fault. Let's take a brief look at the Cascadia subduction zone, a convergent plate boundary that affects California. 2 of the earthquakes we review today are on the map shown here, though neither are directly related to the subduction zone. Here on the left, we have a map of California, Oregon, Washington, and British Columbia, where the Gorda, Juan de Fuca, and Explorer oceanic plates subduct beneath the North America continental plate. We won't spend time discussing the tectonically controlled vertical land motion, though this animation does show how subduction zones can generate tsunami. However, we can see that the 30 October 2024 Blanco Fault earthquake and the 5 December 2024 Mendocino Fault earthquake are shown on the map as yellow stars, and both of these earthquakes ruptured faults that are transformed plate boundaries like the San Andreas Fault. Where the San Andreas, Mendocino, and Cascadia subduction zone faults meet is called the Mendocino Triple Junction. Speaking of the San Andreas Fault, this is an animation that Dr. Tanya Atwater prepared. This animation shows how the San Andreas was born about 29 million years ago in Southern California and has grown north and south to be the main transformed plate boundary between the Pacific and North America plates. The San Andreas is the main strike-slip fault for this plate boundary system, but there are sibling faults to the west and to the east. For example, many have heard of the Hayward Fault in the San Francisco East Bay, a sibling to the San Andreas. There are 3 types of faults, and these 3 earthquakes that I'm reviewing are each on a different strike-slip fault. Strike-slip faults move side by side, and things that cross the fault, like a stream, may be offset by the fault during an earthquake. Here we see a fence near Point Reyes, north of San Francisco, that was offset during the 1906 San Francisco earthquake on the San Andreas Fault, indicated by the yellow dashed line. Note how the once through-going fence on the opposite side of the fault has been displaced by the earthquake to the right. We call this a right lateral strike-slip fault. After the 2019 7.1 Ridgecrest earthquake, the CGS joined the USGS to document field evidence for the earthquake. We set up the California Earthquake Clearinghouse in Ridgecrest and reported into the clearinghouse each day. The road was offset during the earthquake. The red lines show the edge of the road. Can you tell if this was a right lateral or left lateral strike-slip earthquake? Which direction did the earth move on the other side of the fault?
To the right.
Yes, that's a right lateral strike-slip earthquake. Here's another example of the right lateral strike-slip offset for that earthquake. Here of a stream channel, and we can see that the edge of the stream channel marked in red is offset to the right. We discovered some grooves on the earthquake fault formed when the fault slipped, and these grooves tell us how the fault moved. We can see that the fault moved mostly horizontally, but it also has some vertical motion. So for the first earthquake, the December 2024 5.7 Parker Butte, Nevada earthquake, about 8% of the North America Pacific plate boundary relative motion is accommodated on the San Andreas and all sibling faults west of the Sierra Nevada. And then about 15% of the plate boundary relative motion is accommodated along faults on the east side of the Sierra Nevada, along the Eastern California shear zone and the Walker Lane. However, these right lateral strike-slip fault systems are not through-going, and there are blocks that rotate within these fault systems. This magnitude 5.7 earthquake sequence happened at the intersection of 2 faults in one of these complicated areas. So we can look at the lower right diagram to show how right lateral shear causes fault blocks to rotate in a clockwise fashion between 2 right lateral fault systems. As these blocks rotate, they generate left lateral faults on their northern and southern boundaries. The 5.7 earthquake, that yellow star location, is in the Carson domain, where there are also clockwise rotating blocks forming these left lateral strike-slip faults. This map shows the active faults in the Walker Lane. There are right lateral strike-slip faults in purple, extensional normal faults in green, and left lateral strike-slip faults in orange. The red arrows show GPS motion vectors relative to stable North America far to the east. And note how 3 left lateral strike-slip faults, the Olinghouse, Carson, and Wabusca lineaments. The 5.7 earthquake appears to be related to the Wabusca fault in blue. In this poster, I plot seismicity and the USGS active fault and fold database. Note the Olinghouse, Carson, and Wabusca fault zones. The intensity map in the lower right shows felt intensity of MMI6, and the liquefaction, the USGS liquefaction susceptibility map shows a low chance for liquefaction. The aftershock map in the upper right shows that this 5.7 sequence occurred at the intersection of 2 fault systems. The main seismicity trend is along the left lateral Wabusca strike-slip fault, and there's also a seismicity trend oriented along the northern terminus of the right lateral Wasuq Range fault zone. Now on to the Blanco fault earthquake. The tectonics of the Northeast Pacific are dominated by the Cascadia subduction zone, a convergent plate boundary. However, there are additional plate boundary faults in this region. The oceanic spreading ridges, where oceanic lithosphere is created, sources for the Explorer, Juan de Fuca, and Gorda plates. There are also transformed plate boundary faults like the Blanco and Mendocino faults, both right lateral strike-slip earthquake fault systems. The October magnitude 6.0 earthquake represented slip on the Blanco Fault. Brunnemoller and Nabalek from Oregon State University studied the Blanco Fault system. Part of their study included an evaluation of the earthquake mechanisms for earthquakes here. Just like along the Walker Lane east of the Sierra, there are minor complications along this plate boundary, but the big picture is that there are right lateral strike-slip mechanisms along this entire fault. Here's the mechanism and location for the magnitude 5.7 earthquake. All one really needs to know about this symbol is that if it looks like a checkerboard, like in the legend, it's a strike-slip earthquake. Here's a map showing a summary of historic seismicity along the Blanco Fault. The mechanisms, I include mechanisms for some of the major earthquakes, and they all represent right lateral strike-slip fault earthquakes. The map on the right shows the shaking intensity using the modified Mercalli intensity scale, and the lower right plot shows ground motion models in intensity as the green and orange lines, and USGS Did You Feel It results for this earthquake as colored dots. It is far offshore, so the felt reports have low intensity, mostly MMI 1 through 3. On now to the Mendocino Fault earthquake. The Mendocino Fault is a right lateral transform plate boundary separating the Gorda and Pacific plates. There have been historic earthquakes along this fault system. While strike-slip fault earthquakes can generate tsunami, especially if the earthquake slip is shallow or surface rupturing, they are generally smaller in size compared to subduction zone earthquake-generated tsunami. This map is from Lori Dengler et al. And shows earthquake mechanisms associated with the 1994 magnitude 7.1 Mendocino Fault earthquake and aftershocks. The 2024 magnitude 7 earthquake is the largest earthquake along the Mendocino Fault since 1994. What do the checkerboard-looking beach balls represent? Yes, a strike-slip earthquake. These 6 earthquakes all have strike-slip mechanisms that can be interpreted to represent right lateral strike-slip earthquakes on the Mendocino Fault. Here is a map where I plot the aftershocks of the 2024 earthquake in orange and from the 1994 earthquake in green. In the upper right plot, we see higher intensities modeled and observed for this earthquake compared to the Blanco Fault event. The 7.0 earthquake has a larger magnitude and is closer to land where people are than the Blanco Fault earthquake. The map to the right shows intensity observations up to MMI 7.9. That's really strong. The USGS ground failure maps in the lower right show the probability of earthquake-triggered landslides on the left and earthquake-induced liquefaction on the right. We'll take a look at those later. This larger scale map includes the aftershocks and earthquake mechanisms from this 7.0 earthquake sequence. Most of the mechanisms show that these events are largely right lateral strike-slip fault earthquakes. There was a tsunami observed at the North Spit and Arena Cove tide gauges in Humboldt Bay and near Point Arena. The dark blue line on these plots is the tidal forecast, which may be hard to see. The medium blue line is the tide gauge observation, and the light blue line at the bottom is the difference between the forecast and the observation. This signal represents the tsunami and any other background waves. The tsunami was small, on the order of centimeters in size. However, there were observations that the north part of Humboldt Bay emptied and filled at least 3 times. This video shows the change in water surface elevation in excess of 1 meter, a range not recorded on the tide gauge. This appears to be evidence for a seiche driven by resonance from the seismic waves, but we're still working on this, and we need observations from South Humboldt Bay to verify this seiche hypothesis. The California Geological Survey Strong Motion Instrument Program, the CSMIP, runs strong motion seismometers statewide. Along with other network contributors, these data are submitted to the Center for Engineering Strong Motion Data, and anyone can download these data for visualization or analyses. The plot on the left shows the daily download of these data following the earthquake. The ground motion model derived estimate of peak ground acceleration is plotted on the left as a blue line with uncertainty range and with a dashed blue line. Instrumentally recorded ground accelerations are plotted as black dots. And note how the observed ground accelerations are higher than the model estimate within 100 kilometers of the epicenter. This USGS simulation of seismic waves may help explain these higher accelerations due to the amplification of ground accelerations within the Eel River sedimentary basin, though there may be other reasons. The CSMIP engineers have evaluated the ground motion data from sensors in this bridge near Rio Del, east of the epicenter. Well, everything's east of the epicenter. The next slide includes an animation from sensors in the bridge decks shown at the right. This animation shows the accelerations recorded along this section of the bridge, and the plots above show acceleration in units of G, and each plot has a different vertical scale. The two stations on the far right show accelerations exceeding 1 G. Following significant earthquakes and tsunami, the state geologist Jeremy Lancaster sends geologists into the field to make direct observations of fragile, perishable features that are evidence of earthquakes and tsunami. These observations are recorded on mobile devices and included in a GIS database for the event. The CGS used information such as the USGS ground failure maps on the left to prioritize regions for these field investigations. Kate Thomas at the California Geological Survey is the chair of the California Earthquake Clearinghouse, which has managing partners shown below, and a virtual clearinghouse was activated during this event. More information about the California Earthquake Clearinghouse can be found at californiaeqclearinghouse.org. This map shows the locations of observations made from the event response team. Symbols represent the type of observation made. During the event response, the CGS has staff scouring social media for observations, and these data are also included in the database with symbols of colored flags on the map. All of these observations are viewable at the OES, California Governor's Office of Emergency Services State Operations Center via an interactive dashboard. This allows emergency response to be educated about the physical impacts of these natural hazards events. Let's look at some examples. At this location, the circle in red, we can see landslide headscarps. This is evidence for earthquake-triggered gravitational collapse of the road prism. At this location, there was damage during the 2022 Ferndale 6.4 earthquake. The county road department patched the cracks and headscarps, and the photo shows that these cracks, etc., were reactivated during the Mendocino Fault earthquake. Gathered by the social media team at the CGS, these photos were posted by a local news organization to their social media page, and these were taken at the market in Shelter Cove. Finally, final example, these photos show earthquake-triggered landslides along the coastal bluffs near Centerville Beach. Someone might ask, are these earthquakes causally related? Well, in general, there are different ways seismologists think that earthquakes on one fault can trigger earthquakes on another fault. There's dynamic triggering. This can happen when seismic waves from a source earthquake travel across another fault and trigger an earthquake on that receiver fault. This probably did not happen as these earthquakes happened at different times. Then there's static triggering. This can happen when a source earthquake increases the stress in the adjacent lithosphere, leading to rupture on a receiver fault. Seismologists conventionally think that this type of triggering is limited to within 2 to 2.5 times the source earthquake ruptured fault length from the source fault. Using fault scaling relations, the Blanco Fault earthquake may have ruptured a fault with a length of about 7 kilometers, so might affect earthquakes up to about 20 kilometers away. The Mendocino Fault earthquake is 400 kilometers away, so it was unlikely affected by the Blanco Fault earthquake. Using the same scaling relations, the Mendocino Fault earthquake may have been on a 50-kilometer long rupture, and this might affect faults as far away as 150 kilometers, and the Nevada earthquake is too far away. However, there are faults closer to the 7.0. Civilian et al. Used modeling software to evaluate the static changes in Coulomb stress as exerted onto receiver faults by the Mendocino fault earthquake. On the left is shown changes in stress imparted onto faults like the San Andreas fault, showing the San Andreas fault located onshore in this location has an increased stress in red. On the right is shown changes in stress imparted onto faults like the Cascadia subduction zone, showing that the megathrust fault has an increased stress. These changes in stress are very small compared to the overall stress budget for the earthquake faults. Therefore, the faults need to be already highly stressed for them to be triggered like this. And thank you for that. I will now switch presentations, and hopefully nothing embarrassing comes up on my screen. And we'll go to the tsunami talk. We'll start presentation. Okay, Todd Becker is helping support wildfire response at the California Governor's Office of Emergency Services, so I prepared and am giving this presentation. The California Geological Survey and the California Governor's Office of Emergency Services comprise the California Tsunami Program. During tsunami events, we work together with the National Tsunami Warning Center and Coastal National Weather Service Weather Forecast Offices, WFOs, to provide guidance to the first responders that have authority to respond to tsunami events. And we'll review this process for the December 2024 Mendocino Fault tsunami event. First, we'll review some tsunami basics. Then we'll review the response protocol for federal, state, and local agencies and organizations. And finally, we'll take a look at how the response played out for this Mendocino Fault earthquake. Jay already reviewed the basics of the Cascadia subduction zone. In this slide, we'll focus on the tsunamigenesis, the creation of tsunami from the subduction zone. Between earthquakes, the fault is locked. It's stuck like Velcro, and the fault is locked. The North America continental plate is pulled down like a rubber flip-flop, and the island with the tree subsides. When the stress is greater than the strength of the fault, the Velcro, the fault slips, and we get an earthquake. So between earthquakes, the interseismic period, the island goes down, and during an earthquake, the co-seismic period, the island goes up. As the crust deforms during an earthquake, it can lift up the water column where it has gravitational potential. Then the water falls down and with momentum falls below sea level. This pattern of up and down continues and is called a gravitational oscillation, which is the source of energy for a tsunami that radiates outwards. However, the M7 earthquake was not on the subduction zone, but the strike-slip Mendocino fault. This map shows the main subduction zones around the Pacific, and these blue rectangles are the tsunami sources used to model tsunami waves. And these, the model results from the NTWC are the principal basis for tsunami notifications. Subduction zone source seismogenic tsunami. The subduction zone offshore of Chile has an historic record of earthquake-generated tsunami. The maps on the left use color to represent maximum tsunami sizes for 3 historic earthquakes in Chile. The largest magnitude earthquake ever recorded instrumentally, an M9.5 earthquake in 1960, generated a trans-Pacific tsunami that impacted much of the west coast of the US. Here's an aerial image of the coast of Chile from before the 1960 earthquake. Note the trees along the river in the upper left, because here is an aerial image from after the earthquake and tsunami, and we must note that this is not an uncommon impact for tsunami. This is an example for a local tsunami, one that is sourced from a tsunami nearby. Well, strike-slip fault earthquakes can also produce tsunami, though they're generally smaller in size compared to subduction zone tsunami. Here in the upper left is the tide gauge record showing the small tsunami from the 1906 magnitude 7.9 San Francisco earthquake. The tsunami starts at the red arrow. The animation on the right shows a simulation of what the tsunami may have done given what we think about how the fault slipped. However, strike-slip earthquakes can generate larger tsunami. In 2018, there was a magnitude 7.5 strike-slip earthquake in Indonesia. Here we can see the large tsunami generated by this strike-slip earthquake in Palu Bay. On the left is a map with point locations with color showing the run-up elevation over 12 meters or 40 feet in places. And on the right are additional plots showing run-up elevations up to more than 8 meters in places. These are just two different studies. In addition to earthquakes, tsunami are generated by meteorological events like atmospheric pressure changes, storms, and phenomena that we have yet to fully understand. On average, there are about 25 tsunami along the east coast of the US every year. Most are less than 1.5 feet high. Landslide generated tsunami. In 1958, there was a magnitude 7.8 earthquake on the Fairweather Fault, a strike-slip fault in southeastern Alaska, which triggered a landslide causing a tsunami. Landslide generated tsunami can be very large in size, but are limited to the region that they impact due to the length scale size of the landslide. While this 1958 tsunami was large in Lituya Bay, it did not extend significantly beyond the coastal waters of Alaska. Here's a map of Lituya Bay, Alaska, with a superimposed 1958 landslide scar in red at the head of the bay and the forest trim line in yellow showing the tsunami run-up. Note the forest destruction to a maximum run-up elevation of 524 meters, half a kilometer, on a spur ridge, and a maximum inundation of 1,100 meters from the high tide shoreline at Fish Lake. And here we can look at an aerial image showing the erosion of the trees from that tsunami. Half a kilometer. Well, volcano-generated tsunami. About 6% of all tsunami over the last 400 years have been generated by volcanoes, and most volcanic tsunami impact the region near the volcano, like landslide-generated tsunami. Some can have a global impact, like the 1883 Krakatau or 2022 Hunga Tonga eruptions. Speaking of Hunga Tonga, the 2022 volcanic eruption unleashed a violent underwater eruption. It was one of the largest volcanic explosions of the instrumental era and also caused atmospheric pressure waves that circled the globe several times. The volcanic eruption generated tsunami that traveled across the Pacific Ocean, and the atmospheric disturbance generated tsunami in the Caribbean and the Mediterranean. Even though the tsunami size was small in California, it generated strong currents that caused millions in damage throughout the state. On left, we see engineering geologist Nick Grail inspecting some damage of the dock at Moss Landing. And on the right, we can see a blue dashed line that shows that the tsunami reached the level of the floors of some of the restaurants at the Monterey Pier. Well, there's an influence of the tide on the size of a tsunami, and this can be significant. These are both Crescent City tide gauge plots, one for the 2022 Tonga tsunami on top, and one for the 2011 Tohoku, Japan tsunami on the bottom. The vertical axis is elevation, or tsunami size, in meters, and both plots use the same scale. The smaller Tonga maximum tsunami size happened at high tide, while the larger Tohoku tsunami size happened at low tide. Note the difference in maximum elevation and compare with the amplitude. The 2022 maximum elevation is 3 meters, and the 2011 maximum elevation is 2.2 meters. But the 2022 wave amplitude was 1 meter, and the 2011 wave amplitude was larger, twice as large, at 2 meters. So the tide can be significant. Well, how do we educate the public about tsunami hazards in advance of a tsunami? When we're in a tsunami evacuation or hazard area and we receive an official or a natural warning, like a large earthquake, we use the evacuation maps to help us learn where to go to avoid harms caused by tsunami waves. Evacuation maps show the tsunami hazard area in one color and the area outside of the hazard area in a different color. To avoid harm from a tsunami, move outside of the tsunami hazard area. Tsunami hazard area maps are available at tsunami.ca.gov. Now let's learn about the federal, state, and local tsunami event procedures, response procedures. What happens when there's a tsunami? Well, it depends. What happened during the December Mendocino Fault earthquake generated tsunami? Well, it's complicated. Recently, members of the California Tsunami Program took part in a training from the National Tsunami Warning Center in Palmer, Alaska. We learned about the process that the NTWC uses to respond to tsunami events. We will review this and discuss how this process took place last December, which involves actions from both the NTWC and the CTP. This map shows the area of responsibility for the NTWC in red and the Pacific Tsunami Warning Center in orange. Californians want to pay attention to the alerts from the NTWC, and alerts are all posted to tsunami.gov. Well, there are 4 levels of tsunami alert that the NTWC or PTWC may announce. This graphic shows the alert level in red, what action is suggested, the type of hazard, and the general size of the tsunami. The tsunami advisory in orange is issued when the tsunami forecast amplitudes are 0.3 to 1 meter in size, and a tsunami warning is issued when the tsunami forecast amplitudes are greater than 1 meter in size. When an earthquake occurs, the NTWC must decide within 5 minutes if they need to push out a tsunami information, watch, advisory, or warning alert. First, a duty officer uses the seismic waves to calculate a magnitude, earthquake magnitude, while at the seismic station. Then they move to the tsunami station, different workstations. Depending upon the magnitude and location, their protocol may require the NTWC to place regions in a specific tsunami alert level. The duty officer at the tsunami station then uses initial earthquake parameters from the seismic station to forecast tsunami arrival times and amplitude estimates to assign to forecast points. This ATFM tool sets the level of tsunami alert for regions along the coast. Then the duty officer uses a tsunami numerical model calibrated by tsunami observations from dart buoys to forecast tsunami forecast amplitudes with higher confidence. And then the CTP, California Tsunami Program, use these high confidence tsunami forecast amplitudes in their faster playbook approach to provide recommendations for tsunami evacuation levels to coastal counties. And we'll go through that in more detail. State is subdivided into regions, and each potentially with their own alert level. These regions are separated by breakpoints, and there are only so many breakpoints. Here's a map showing the regions separated by the breakpoints, which are blue dots, as well as on the left, the list of locations for which there are tsunami amplitudes forecast. Note that there is a breakpoint at Gualala, the border of Mendocino and Sonoma counties, and a breakpoint at Davenport, north of Santa Cruz. The NTWC treats everywhere between these 2 breakpoints with the same tsunami alert level. Here's the general timeline for tsunami response collaboration between the NTWC and the CTP. This process is designed to work for distant tsunami sourced far enough away that there is time for official notification and evacuation. First, the NTWC detects an earthquake. Then they send out alert message number 1. The magnitude and location may put some coastal regions into a watch, advisory, or warning as part of this message. For warning, advisory, and watch level events, where the ATFM model results are incorporated, first, the NTWC, the state, and the weather forecast offices hold the first conference call to discuss the tsunami event. A half hour later, the state and the counties, coastal counties, hold a conference call to discuss the tsunami. Continued NTWC alert message and hourly conference calls proceed throughout this entire process. The NTWC will process available data from the buoys. This is the SIFT modeling. And then the NTWC sends alert messages with forecasts for wave amplitude and time of arrival. Then the state and the National Weather Service use the faster calculation, which I'll talk about later, to generate recommended levels of evacuation for each county. And then the NTWC, the state, the weather forecast office conference call takes place to discuss the tsunami forecasts from the SIFT modeling. And then half hour later, the state county the state and coastal counties have a conference call to discuss recommended levels of evacuation for their evacuation plans. At some point, the tsunami arrives, and the state will be available and provides updates throughout the event with hourly calls until the tsunami event is over. And the NTWC will cancel tsunami alerts once there is negative evidence for the tsunami that the tsunami is observed. So this process is useful with sufficient time to make official announcements and to evacuate. This is true for tsunami from around the Pacific. These are some travel times. These orange lines are some travel times from different places relative to Crescent City. We can see the tsunami from Alaska may arrive in as little as 4 hours, and from northern Chile in as little as 13 hours. And here are some travel times from different places, or the same places relative to Los Angeles. So Los Angeles is about 6 hours from Alaska. The NTWC tsunami alerts are subdivided based on tsunami size. Because not all tsunami are large enough to flood the entire tsunami hazard area, local emergency managers request the CTP to prepare a phased level of evacuation based on these different tsunami level alerts. This allows them to evacuate fewer people for smaller tsunami events. This phased approach uses what we call tsunami playbooks to help recommend the extent of evacuation that local emergency managers should consider. The tsunami playbook approach uses tsunami forecast amplitudes from the NTWC from their alerts and real-time sea state conditions to prepare a recommended evacuation area, such as a phase 1, 2, 3, or maximum phase. And here's a map showing how the maximum phase is the largest evacuation area based on the statewide tsunami hazard area maps recently updated. In this region, we can see that a phase 2 evacuation involves many fewer evacuees. This slide details all the factors that go into a software program that the CGS and the Monterey National Weather Service Weather Forecast Office prepared. And the software basically takes the forecast amplitudes from the NTWC, adds things like tides and storm surge and some other information to calculate the total water level at those forecast locations. And the software outputs the recommendations for each county. And then since counties hold evacuation authority and they choose their evacuation response, the recommendations are minimum evacuation recommendations, and the counties can choose to evacuate larger regions than recommended. Here's each county has a set of tsunami evacuation playbook maps, and this is an example. And this map shows the footprint for each tsunami evacuation playbook in the state. So the Mendocino fault tsunami process only got to an early step at the tsunami event, ended with the first conference call between the NTWC and the states and the WFOs, that yellow star, orange star. So just a couple more slides. Here's the event timeline. At 10:44, drop cover and hold on, as I did, because I felt the strong ground shaking. And 5 minutes later, the NTWC sends out tsunami warning message number 1. The area covered by the tsunami warning, the placement of these areas into a warning alert is based on the operations manual procedures used by NTWC prior to any tsunami modeling used solely on magnitude and location. The initial magnitude was determined by the seismic station, and there are some arrival times for some locations. At 11:24, NTWC sends out warning message number 2. The magnitude is updated, but nothing else changes because there are no observations yet. And then warning message number 3 at 11:54, the warning is canceled because a tsunami was observed on a tide gauge showing an amplitude smaller than 0.3 meters in size. The tsunami alerting protocol for this earthquake was to include a tsunami warning alert for locations within 250 kilometers of the earthquake. The 250-kilometer distance extended just past the Gualala breakpoint. This is the reason the entire area between Gualala and Davenport were included in the tsunami warning, including San Francisco Bay. And the CTP has been asking the NTWC to add a breakpoint at the Golden Gate for over a decade, but the NTWC cannot yet do this. So what went well? Immediate notification went out via wireless emergency alert, and people followed the instructions in the message. There was successful collaboration between agencies. There was successful evacuation of beaches, and there is an increased motivation to develop an update plan specific to local tsunami source incidents. Areas of opportunity for improvement. WIA messaging. We need to update the WIA alert language to provide clearer guidance and remove alarming language. We need to increase the number of breakpoints along the West Coast to enable alerting to the areas of potential impact, especially that inside San Francisco Bay may be different. Excuse me, we need to update tsunami warning system to narrow WIA alert distribution using polygons that National Weather Service and National Tsunami Hazard Mitigation Program partners have prepared. And there's also no tsunami warning cancellation sent out via WIA. So the responsibility falls on state and local entities to provide tsunami warning cancellation and all clear through other means. Finally, there's significant milling time observed for those evacuating. Most evacuees do not evacuate on foot and use their cars, which is not a good idea. And many driving from high ground drove through potential hazard areas. Also, upon receiving WIA, many went to tsunami.gov to look for evacuation information, but evacuation and hazard area information are not available at tsunami.gov. They are available at tsunami.ca.gov. And with that, I would like to finish my presentation.
Thank you, Jay. Let me say this, you covered a lot of material and your slides were excellent. I for sure will review them. There's so much material there. So thank you very much.
Thank you.
Now we do have questions and I'll pose them to you and hopefully you'll be able to answer them. Okay.
Great.
The first question is, do ongoing events like the Blanco Fault load the stresses on the Cascadia subduction fault that's locked?
So that's a good question. Oh yeah, that's a good question. I often get that question, and it depends on the magnitude. If there was a magnitude 7.0 on the eastern part of the Blanco Fault, that could affect the subduction zone. But we haven't seen a magnitude 7.0 in historic times, though it definitely could happen. Most of the earthquakes that we've seen in the historic period are magnitude 5s and magnitude 6 earthquakes, and so they're just too small in magnitude.
Okay, very good. Next question. This has to do with spectral accelerations that were recorded onshore. In other words, the question deals with the motions that might have been recorded from the December 5th event with the design spectra that's from like ASCE 722. Okay, do you know anything about this, or can you comment?
I'm going to ask the person to follow up with me in an email, and I can direct them to Hamid Haddadi, who runs the California Strong Motion Instrument Program, and he will be a much better person to respond to this question.
Okay, very good. Next question. How are California communities mitigating against tsunamis in the built environment? Are they building new construction above the tsunami regions?
So in California, many lead agencies, so cities and counties, have adopted the into the California Building Code, ASC 716, Chapter 6, which are tsunami loads and effects. And so for tsunami risk category 3 and risk category 4 structures, like hospitals and police stations, fire stations, they are required to design those structures to mitigate the loads and effects from tsunamis at the 2475 or the 2% and 50% and 50-year probability events. And the state of California has, based on probabilistic tsunami hazard assessment, has the suite of 2475 tsunami models that had been adopted by ASCE. So if someone were to put into their internet search bar ASCE tsunami design tool or a tsunami design zone, they will find a website where they can look up the 2475 tsunami footprint, and they can use that tool to help calculate those loads and effects.
Okay, very good. The next one deals with the a news item that was in the Bay Area. And the question is, why did Berkeley, the city of Berkeley, issue a mandatory evacuation order for everyone west of 2nd Street? Can you comment or know anything about that?
So I'm unfamiliar with the geography of that specific geography of Berkeley. But I will remind everyone that the local emergency managers at cities and counties, they're the ones that have the authority to evacuate people. And I can hypothesize that the reason that they evacuated people is because Berkeley was within the tsunami warning alert. Now, I discussed the reason why San Francisco was placed into a warning is because the 250-kilometer distance from the epicenter went just past Gualala. And so this is an area that we are trying to work with the NTWC to maybe, update their protocol, because there probably was no need for the San Francisco interior bay to be placed into a warning. But it was difficult at the time. The NTWC has these protocols, and they do have evidence for tsunamis of that magnitude elsewhere in the world generating tsunami. So, things will get better as we go through.
Okay, very good. Next question. Many people on the bay side of the San Francisco Bay Area, that's inside the bay, were confused by the messaging. And you've acknowledged that the messaging needs improvement in the future. Could you talk in general about the potential run-up inside the San Francisco Bay for major tsunami events?
Yes, so the tsunami hazard area that we work with each county to develop, because they have the authority to create evacuation maps. So the tsunami area within the San Francisco Bay and most of the state of California is based on the 975 tsunami, the 10% and 50-year probability tsunami model that we have. And so if you look at that tsunami model, the result, that tsunami model, you'll see that, and anyone can download the PTHA data, the 975 tsunami model data from tsunami.ca.gov. And if you look at those data, the size of the tsunami before it enters the Golden Gate is 7 or 8 meters in amplitude, and once it goes through the Golden Gate, it is restricted and diminishes in size to between 4 and 2 meters in amplitude. So places like San Rafael, the tsunami size has about a 4-meter amplitude, and then once you get up to Petaluma, the tsunami amplitude is closer to 2 meters. For the 1,000-year tsunami, the 975 tsunami.
Okay, very good. Another question is, and I think you may have mentioned this, but you might have talked about this, but I'll ask the question anyhow. Can we obtain the maximum potential tsunami and inundation elevations? And then it goes on. In 2011 at Tohoku, one location was overtopping with many facilities to those climbing to the roof of the structure. So the question again has to do, where can we obtain maximum potential run-ups? And I think you mentioned that somewhere. Go on.
Yeah, so if you go to tsunami.ca.gov and you scroll down to the reports page and you go to the reports and data page, you can download. We posted there on our box.com account the data set, so anyone can download the tsunami models at 72, 100, 200, 475, 975, 2475, and 3,000-year return periods, and each of those have their own probabilities of exceedance. And so the maximum that we have is a 3,000-year tsunami, and people can download those, and we have flow depth data, we have amplitude data, we have velocity data, and we have momentum flux data. So that's where I would direct people, and people can, if anyone wants to follow up with in the emails, please send me an email and I'll put that in the chat.
Okay, great. Next question. This has to do with earthquake damage. You know, in Northern California, there's that small town of Petrolia, and that was close to the coast. And I believe some of the strongest ground motions were recorded there. Are you listening, or?
Yeah, I'm listening.
Okay.
Yeah.
Well, do we know much about the damage? That is, ground motions apparently were strong there, but didn't seem to cause much damage there. And I realize Petrolia is pretty small.
Yeah, my colleague Thomas Dunklin lives down there in Petrolia, and lots of things were, you know, thrown off the shelves, but his lives in a wood frame structure building, which typically perform really well. I don't know of any unreinforced masonry buildings in Petrolia. His dog definitely was shook up in many ways by the earthquake. So why? Like the 6.4 Ferndale earthquake, December of 2022, had really large accelerations observed in Rio Dell and Fortuna and Ferndale, and they were the highest observed accelerations recorded by the Strong Motion Instrument Program ever. And so I think one of the stations recorded in Rio Dell of 1.4 G or something like that. And in the same stations, which are not as close to the earthquake as Petrolia, in the same locations, Fortuna, Rio Dell, Ferndale, this Mendocino Fault earthquake recorded about 0.4, 0.3, 0.4 G. So it was much lower in acceleration. And we think two reasons for that. One, the 7.0 was further away, so it was further offshore, even though it was a larger magnitude earthquake, it was further offshore. And then also the type of rock that was ruptured. So the Ferndale earthquake ruptured the Gorda crust, the Gorda plate, which is peridotite, really hard rock. So there was a big stress drop. That was a high stress drop event. Whereas the Mendocino Fault earthquake 7.0, one side of the fault is the Gorda plate, but the other side of the fault is an ancient subduction zone. So it's a different type of fault, a different type of rocks. And so that may have also contributed to the difference in.
Excellent. Jay, look, let me give you a compliment. We've got a few more questions here, but you're doing an excellent job on these questions. My compliments. You're able to answer them quite succinct and satisfactory. You know, but here's a simpler question here. Okay. It seems like seismologists, every time we have an earthquake in California, major earthquake, the seismologists always say they're surprised. Oh, there was some aspect on this, or this happened. What was there anything surprising from a seismological point of view about this earthquake?
Oh gosh, you know, the easier questions are harder to answer. Yeah. Well, of course, the reason why we're surprised often is that we have such a short record of observations. I mean, some of these faults, you know, have really long return periods, and there are earthquake super cycles. So we really need, you know, tens of thousands of years to really observe the full spectra of earthquake fault behavior.
Okay, that's fine. I don't want to take your time.
There was a tsunami. So tsunami, from the tsunami perspective, the earthquake was really interesting because it was in Humboldt County, where I live, it was both a local event. So we have the natural warning, which is the earthquake, and it was we also got the official warning, so which is typically what we get for distant events. So people in Humboldt County were kind of confused by that. And that's why we saw, I saw people driving. So I live on the North Spit, which is a sand spit on Humboldt Bay. And people should have used their training to go to high ground. But then they got the official warnings, which led them to drive off of the North Spit. And if there was actually a large tsunami from this event, they would have not had a really good experience in their cars because they would have been in the tsunami, sadly. So, yeah.
Okay. Okay. The final question is this. Now, with these warnings, do you know at what level is Governor Newsom informed? In other words, you mentioned everything's happening pretty fast. These signals come in. Was the governor, how soon before he would be alerted to this?
So the state geologist, Jeremy Lancaster, was on the phone with someone from the California Governor's Office of Emergency Services within a few minutes, half dozen minutes. And the governor was on that call. And so he, the California Geological Survey provides, within 15 minutes of an earthquake, we provide what we call earthquake quick reports to Cal OES, and those, when they're specifically larger events, those go right up the chain to the governor's office. And so the governor, really has their finger on the pulse of because the Cal OES, that's their office. So they are kept in touch really quickly.
Okay, so he was informed very quickly. Okay, great. That's all the time we have for questions. There might have been a few more, but I'll ask the person to email Jay directly on those, because we need to be wrapping up. We're reaching our time limit here. So I'd like to thank Jay for a very informative presentation. Your slides were excellent. I will make a point of reviewing them in detail. There's so much material there. Now what I'd like to do is conclude my portion of today's meeting, and I'd like to return control to Richard McCarthy, our president, to say a few words. Richard, could you please tune in?
Thank you, Jay, very much. That was really, really fantastic. I'm very impressed at how the state and the USGS has advanced our tsunami warning knowledge and our knowledge of reporting earthquakes and how they occur and potential damage. I'll end this with saying, I think what's going to happen now, since these fires in Los Angeles, the governor's issued 2 new executive orders on recovery, rebuilding, and that's going to be a game changer in how we recover from all the natural disasters, I think, here in California. So anyway, thank you very much, Jay, and I'm going to turn this over to Elizabeth.
Great. Thank you, everybody, for participating in this webinar. We'll share the recording on the account within a week or so. We should have it up. So go to our YouTube account for EERI to see that. A post-webinar survey is going to pop up on your screen when we close this in a second. You'll also get that by email tomorrow. And we'd appreciate it if you took the time to fill that out and give us feedback. You can learn more about EERI at our website and join us at that link. And find out information on upcoming webinars. We're also just wrapping up our end-of-year drive for the LFE endowment. So there's a link for donating. And finally, I just want to once again thank our sources of support for this webinar series, FEMA, the LFE endowment, and our EERI membership. Thank you, and I hope to see many of you next week at our Spectra webinar.